Hello, my name is Daniel Wortmann, and in this short presentation I would like to discuss the parallelization strategies of the FLEUR code. So in particular I want to address the question why FLEUR is so slow or so fast in some situations, and in particular what you can do in order to make sure that for your system you want to simulate FLEUR runs efficiently and runs fast on your available computing hardware. Okay, the first question we have to answer is probably why we at all bother talking about this. And the basic problem we are facing is that we have to match our simulation problem somehow to our available computing resources. And this can be of course, rather difficult because there can be very different systems you want to simulate, and there can be very many different computing resources you want to use. And a particular problem is, of course, the question of scaling and the question of time you need for your simulations. And there, the first thing I would like to remind you of is that a typical DFT code and also FLEUR essentially scales roughly cubically with the system size in terms of the number of atoms when it comes to its execution time. So essentially your computing time requirements scale with the cube of the number of atoms. The memory usage scales better, it only scales quadratically. But what does it mean? If you think about it, if you think, for example, you wouldn't like to calculate on a single core of your computer, and you have a system with, let's say, 64 atoms, and the simulation might take an hour and take something like 2.5 GB of memory or so. And then you can think what happens if you now use larger systems. You want to simulate perhaps 256 or 512 atoms, and you can see that the execution time here in this column here grows significantly, and it essentially looks like the code is actually not able to do that in any reasonable amount of time and using any reasonable amount of memory here, right? But now, of course, you know that the assumption we made here that we calculate in a single core is not really what we have in current hardware. I mean, even modern laptops, even the laptop you have there at office or at home, probably has the number of cores, so something like 8 or so. It might have something like 32 GB of memory. You might have a workstation in your office which has a few more cores and even more memory. Or you might even have access to a supercomputer where you have thousands of cores and many terabytes of memory. And now the question is, of course, how can we use them efficiently? Now you might say, oh, this is not really my problem, right? All my physics problems can be described by a few small systems. I don't want to bother with all these strange supercomputers, so I don't have access to them anyway, and I want to run on my laptop or my workstation, and that's completely fine with me. But even then, you see already that you have to think about these problems, because your laptop and also your workstation will not simply have a single core, a single unit which can execute the program, but will have a few or many of them, and you have to know how to efficiently utilize your computer. Okay, so before going into the details, what we do in FLEUR, perhaps we should have a short introduction and a very simplified view on basic hardware architecture, so that we are all on the same footing when it comes to the questions we discuss later on. And what you have to know essentially is that each modern computer nowadays has a processor, a CPU, which consists out of many computational cores. Right, and this core access then the memory of your computer, this is true for essentially everything you buy and which can compute currently, from your laptop to your smartphone or tablet or whatever computer you might have in your office, right? So you have multiple of these cores which can be used to execute your program, and these usually access the same memory on your computer, and this is called shared memory architecture, and this is something we will discuss a little bit more later on. When you then grow and when you have then larger computers, say, let it be a real supercomputer or just a larger compute cluster in your institute or perhaps even at home, what you usually then have is you have many so-called nodes, which are essentially many units of what we just presented the slide before. So many of these computers which contain a CPU with multiple cores and some memory, and these many units, so each of them is called a node. Each of these units here is then connected to all the other units by some kind of network, which might be very fast or might not be so fast. But that's the basic situation. So in contrast to what we had before, we now have different compute units, which these CPUs with these many cores, which access their own memory, right? So they don't share the same memory anymore, but each of these nodes has its own memory, which they can access and use. This short discussion already tells you that there are different paths in order to achieve high performance and scalability of computational code and also of FLEUR. So on the one hand, you have to optimize the performance the code has on the single of these nodes. And on the other hand, you have to make sure that you can use multiple of these nodes and that you essentially can scale up, so use more and more of these single nodes. In FLEUR, we have different strategies for these two tasks here. And we will discuss them in a little bit more detail later on, but just to give you here the summary. On the one hand, we use optimized math libraries to get very good performance on the core. We use something which is called OpenMP for using multiple cores. We also have a implementation for GPUs. GPUs are available on your nodes. We use OpenACC and a bit of CUDA. And we, of course, also try always to change algorithms in order to be as efficient as possible on the single node. On the other hand, we also have multiple levels of parallelism, which we use to ensure scalability over many nodes. And that, of course, includes that we have to talk about the data distribution, which we have to optimize for the different kernels, and we do that using MPI communication, also including so-called one-sided MPI communication. Okay, so just to discuss this in a little bit more detail. So the main two parallel programming frameworks we use are on the one hand OpenMP, which we discuss here, and MPI on the next slide. OpenMP we use for so-called shared memory parallel programming. So that's what we have when we stay on a single node. As we discussed, we have the different cores, so which are depicted here as P, so different kind of processing units. And they all access the same memory, right? And therefore, you can essentially write with one of these processors to some part of the data, and then you use it somewhere else. So parallelism is relatively simple there. It is done using pragmas. If you look at the code here, it looks a bit like this. And the advantage is, of course, there is no explicit communication really going on, because the data is transferred via the memory here between the different processors. And so this can be a very efficient way of programming on a single node. The other parallel programming paradigm we use is so-called MPI programming. There you have explicit communication between these different processes, and they communicate by sending each other messages. So if you have some data attached in some memory, which might be local to one processor here, this is then might be sent in a message to some other memory location where another processor can access this data. And this can be then used in order to distribute your code over different nodes, but of course it could also in principle be used on a single node, right, where this memory in principle would still be shared. With this kind of introduction, I hope that we are on the same footing with regard to these basic ideas of parallel programming and parallel computing and the computer architecture we use for that. And now we would like to discuss a little bit the question of how we actually now do it in FLEUR. So how do we parallelize FLEUR in order to achieve nice performance and nice scalability? Okay, if you look at FLEUR, you see this diagram here with the basic steps which the FLEUR code performs in a self-consistency iteration. So you see we have a setup of the potential, so we calculate the potential out of the density we have. Then we have to calculate the matrices, so the Hamiltonian and the overlap matrix. So there's a setup of these matrices. These matrices then have to be diagonalized, and a new charge has to be constructed out of the eigenstates, right? So here you see several of these blocks here, because this can be done for many k-points, right? The potential is the same for all k-points, but the matrix setup, the diagonalization, and also the charge generation in some sense can be done more or less independently for all these k-points. If you look at the computing time, this is how they scale these different parts here. You see the potential scales essentially quadratic, all the others scale cubically. And usually here, this center part here takes the bulk of your computational time. And therefore, this is, of course, where you have to make sure that this runs most efficiently. We have now several different levels of parallelization in the code. And the first and probably most important parallelization level you should know and you should understand is this parallelization over the k-points. As I just said, these problems here are essentially independent problems. For each k-point, you set up a matrix, you diagonalize it, and you can calculate the charge originating from these eigenstates at that particular k-point. And therefore, we have a loop here which runs over all these k-points, and this loop can be distributed over different MPI tasks. And here we use MPI. So this parallelization strategy, which can also be deployed over several nodes and can be used to distribute the problem over several nodes. We also have a second MPI parallelization where we essentially take the matrix and distribute the full matrix over several processes. The advantage of this is that for larger systems, when the matrix becomes perhaps too large to fit on a single node, you can actually then distribute the matrix over multiple nodes. This can therefore help you with memory, but of course for very large matrices it's also useful for doing an efficient matrix setup and an efficient diagonalization using many nodes. In addition to these two parallelization loops, we also have an OpenMP parallelization in the code. The OpenMP parallelization is somewhat additional to these k-point and eigenvector parallelization, and it is employed in all parts of the code and can be used to use multiple cores on a single node. We also have a vectorization, but we won't discuss this in any more detail here. Okay, from this discussion, you might already have an idea of how these different parallelization levels actually behave and how they scale. And so the first thing we should look at is the k-point parallelization. As said, this is the distribution of the different k-points on a different number of processors. And there we take the most time-consuming part of the code and distributing them on the resources we have. And as you can see here, what you see here is the speed up of the code as a function of the number of nodes. And what you can see here is the ideal speed up would be essentially this line here. And what you can see is that the code really scales very nicely. So we are very close to this ideal speed of here. You can see that it's therefore a very good idea to use this k-point parallelization as much as possible. In order to achieve that, you have to adjust your number of k-points and MPI processes somehow, or let's say differently. Usually you have given a number of k-points you want to simulate, and then you have to choose your MPI processes in a way that you can easily distribute them, right? So if you have 10 k-points, you can use 10 MPI processes very efficiently. You can also use 5 MPI processes, but it's not such a good idea to use, I don't know, 7 MPI processes when you have 10 k-points, because then you cannot really distribute the k-points equally on the MPI processes, and this is something which FLEUR will not do. Okay. The second level of parallelization, as we said, using MPI, is then the eigenvector parallelization, or the parallelization of the eigenproblem. So here we now distribute the matrix, and this allows us to tackle a larger system. But as of course now we distribute the eigenproblem over different processes, this is not as efficient, right? Because now when diagonalizing the matrix, these processes have to talk to each other, they have to send these messages to each other, and this of course leads to a scalability which is not as good as we've just seen. So here on the right hand side you again can see this such a speed up curve here, and you can see that we are not here along the ideal line anymore, but when you use something like 30 processes, you only or 30 nodes here. Sorry, we have many more processes actually, but if we use something like 30 nodes here, we only get a speed of a factor of, let's say, 15 or so. This is not as efficient as we have seen before, but still it scales, so it makes the program faster. And of course, as you can see here, the memory usage goes down. So what you can see here is the number of MPI processes, and here you see the memory which each of these processes needs. And you can see that the larger number of MPI processes is, this memory goes down drastically. Of course, it saturates at some point, because there are, of course, also parts of the code and part of the data which cannot really be distributed, but each process has to have. But you can imagine if you now have a computer which has, let's say, only 8 GB of memory, which of course would be relatively small, you would need at least 10 of these in order to fit your problem on your nodes. Right? Okay, now I would like to continue by showing you an example of how you can use these different parallelization strategies to simulate a real large system. And what we have done here is we simulated what is sometimes called a chiral bobber, a large magnetic structure here, where you have a kind of chiral skyrmion in here embedded in a more or less ferromagnetic material. And this is then kind of stopping here, and you have a special point here called Bloch point. But we, of course, here want to focus on the computational aspect of the system. We calculated the system, which has about 1,000 atoms. It's, of course, a non-collinear setup. Has only a single k-point, so we cannot use k-point parallelization. But nevertheless, we parallelized here using MPI over 256 nodes, each of which has quite a few cores. And as you can see, the matrix is also relatively large here, and this then leads to a calculation which takes something like 25 minutes per iteration. And if you then converge it, it's quite a significant computational time you have used here for the system. You can also see that this green line, this 1000 atom system here, that you can go to even larger system and you still have scalability. So still the runtime decreases significantly when you use more systems, more computational resources here. Okay, this of course now leads us to the very practical question of how do you now really choose your parallelization. So let's start with an example. Let's think of a system. Let's say we have three nodes. Each of these three nodes has 32 cores, so a small cluster, not particularly powerful, but still, I mean. And now, of course, you might have some system, and you might want to put it on that machine, right? And you know there are these different parallelization strategies. There are the MPI task and the OpenMP, which usually are called threads then. And you know that the OpenMP threads can only be up to 32 because they only use shared memory, so they work only on a single node. And the MPI tasks can be here pretty much everything, and every number you want, and you now would think of, okay, how could we parallelize it, right? So we have a total number of 96 cores, and we can of course do something like 3 MPI tasks. That's the minimum we have to use in order to be able to use the 3 nodes. And we can use 32 MP threads, but we can also distribute it somehow differently, the different cores we use. And the question is, how do we actually do that, and what is the best choice? To answer the first question, this technical question is how do we choose the number of OpenMP threads and the MPI processes? And there are two different things you have to do in order to do that. On the one hand, there is a environment variable called OMP num threads, and this has to be set to the number of OpenMP threads you want to use in your system. So, for example, here it's set to 4. So before you start FLEUR, you have to set this environment variable to the correct value to tell FLEUR how many OpenMP threads should be used. MPI processes are started somewhat differently. You have there something like MPI run, which you have to use in order to call FLEUR. So you do something like MPI run minus N4, which then will start 4 MPI processes. Or you might have different commands like srun when you have a queuing system, and there you really have to now look at your documentation of your MPI and of your system in order to understand how to start MPI processes correctly and how to choose the number of nodes there. Okay, but that still doesn't answer the question of how many processes should you really use and how should you distribute it. Usually, of course, it's a good idea to use all the cores you have, right? So you could say you use 32 OpenMP and 3 MPI, then you have the maximum OpenMP parallelization you can have. You could, of course, also say we need all the cores for MPI tasks and don't do any OpenMPs, and you have the maximum of MPI. Or you can do something in between, which also might lead to situations where you actually don't use all the cores, but you have only slightly less number of cores used. So there are, of course, different possibilities, and depending on your system and depending on your computer, all these choices can be efficient, and any of these choices can also be pretty bad. And that depends, as said, on the machine you are calculating on. It also depends on your system you are simulating, so it depends on your mbXML file. We are currently working on a tool called FLEURist, which is supposed to examine now your mbXML and give you suggestions. And you're very welcome to try that out. It's a tool under development. We also have already a small tutorial how this is supposed to be used. Okay. So essentially, this concludes this discussion about parallelization and how to choose your parallelization strategy system. A problem I still would like to discuss a little bit is the question of the GPU, whether FLEUR can use a GPU and why we actually use a GPU and what we do there and what is available and what is perhaps problematic. GPUs are now used very frequently in computing, and the basic reason for that probably is the fact that there is a kind of problem in the scaling of the performance of CPUs, which materialized in the last, let's say, 20 years. So you probably heard about Moore's law, which essentially tells you that the number of transistors grows exponentially with time in a processor. And this is more or less still the case, but what for a long time was accompanying this growth was the fact that although the performance grows exponentially, and that's in some sense no longer true, at least not if you look at the performance of a single computation, right? So this is kind of leveled off. Modern processors, modern CPUs don't really get faster anymore. And we will not discuss in detail here the reasons for that, but the main takeaway here is that computers using just the CPU usually don't really scale so nicely anymore in terms of computational power. There are also questions of performance of efficiency in terms of the power usage and so on. But what then happened is that essentially a new way of computing in HPC evolved, which had some kind of differences compared to standard CPU calculations. And as a result, if you look now at the top 500 list and you look at the top 10 supercomputers, all except one, the Japanese one, all the others use GPUs for processing. So you might now ask what is the main difference of the CPU and the GPU. Essentially, there are a couple of differences in terms of programming these and in terms of what they are optimized for. So CPUs are essentially very general purpose machines or processors which can handle lots of different codes. They have usually a relatively low latency, so they can calculate complex code where which has a lot of branches, where it's not really so easy to see the data flow through. They have fast clock rate, have caches for this, they have very powerful processing units and so on. They usually also, however, have a relatively small memory bandwidth, and it can be very costly if the program does not access the memory, and they have not so high performance per watt, so the energy efficiency is not so high. GPUs are somewhat very different, and they have very high bandwidth memory, and they are optimized for really high throughput, meaning they can do a lot of the same kind of calculations at the same time, right? So it's very good if your calculation, if you have a lot of parallelism, if you have a lot of things to do which are very similar, and you use a lot of data there in order to process this. They usually have, however, limited data. They have also not so high performance if your problem does not look or is not so parallel. So if you have a single thread, a single execution part in your code, then the GPU has much lower performance than the CPU. And another problem they have is usually you have to, in order to use them, you have to transfer memory from the CPU to the GPU, and this can be very slow, and you have to make sure that this is done efficiently and not too often in order to get performance out of these machines using GPUs. Okay, when we now look at FLEUR, so in FLEUR, most of the computational relevant parts are ported to GPU. However, they are only this can only be used currently with NVIDIA GPUs. The reason for that is that you need the NVIDIA HPC compilers in order to compile the code. We use OpenACC, which is a programming paradigm similar to OpenMP, but for GPUs. Essentially the only compiler which supports that sufficiently is so far the NVIDIA HPC compilers. G-Fortran, for example, has so far too little support for this. And therefore, you need the NVIDIA HPC compilers, and the NVIDIA HPC compilers produce code for NVIDIA GPUs, and therefore you can only use NVIDIA GPUs at the moment. The code is also parallelized, so you can use MPI in addition to the GPU version. You have therefore multi-node available. You can use multiple GPUs per node. You can also use multiple MPI processors for GPUs. All this is possible. What is challenging, however, is that the compiler change is quite a lot more complex. When you want to compile the GPU version, you have to deal with having all the correct setup, for example, having the correct CUDA versions. Very often you have to compile relatively basic libraries like BLAS, LAPACK, SCALAPACK, and so on. For your compiler there, it might not be provided. And you also have to compile the LPA library, which is needed for efficient multi-GPU diagonalization. So if you want to use this eigenvalue parallelization, this distribution of the eigenvalue problems on multiple MPI processes, and therefore on multiple GPUs, you need the LPA. And this can be challenging. All this can be challenging to build and get to run. Another challenge is that the GPU has to be kept busy, and this means that when you run on the GPU, you have to make sure that you really have enough computational load on the GPU. Right? It's very bad if the GPU does not have enough data to operate on, because then this relatively low single thread performance becomes very visible, and the code does not really run fast and efficient. So you have to make sure that your system is large enough, your problem is large enough, and that your parallelization is suitable so that each GPU has enough work to do. And that makes the parallelization strategy more difficult than on the CPU, and you really have to test there carefully what is efficient. So will the code really profit from my GPU, and how do I have to set up the calculation in order to get the best performance out of it? Okay, this more or less concludes this presentation. There are a few subjects I have not covered, and I would like to just very shortly mention and give a little bit of advice. There is the problem of thread placement and pinning, especially if you use OpenMP. You have multiple processes running on a single CPU, and you have to be very careful here not to run more than one thread per core. So the efficiency, of course, of this parallelization goes down rapidly if you use a wrong number of threads, or if the threads are not distributed nicely over your cores. And here there is a little bit of output in FLEUR telling you if many cores run on a single many processes run on a single core, and then you should check whether your setup is correct or not. There's also sometimes the problem that modern CPUs, especially in laptops and so on, have different cores. So they have what very often is called performance cores and efficiency cores. And to our experience, it's very bad if you use them together in a parallel setup. So if you have efficiency cores and performance cores, and you distribute your code such that it uses both of them, then usually the code runs as fast as the slowest core runs, right? So which is then usually this efficiency core, and that is not usually what you want to do. And it can be that even if you use more cores, it can be much slower than if you only would use the performance cores. There's also a problem with architectures which are called NUMA architectures, which have non-uniform memory access. So this can happen essentially in your machine, and it particularly usually happens if you have uh, multiple CPUs in your machine. So not a single chip, but many, and then the memory might be attached to one or the other. And if you then access the memory wrongly in a shared memory way, you get a bad performance. And but this is a very advanced topic you have to discuss with your system administrators, probably how to do that very efficiently. And the last thing you really should care about is that you really make sure that you use optimized libraries, especially that you use optimized libraries perhaps provided by your compiler vendor or vendor of your machine for the linear algebra, for the BLAS and the LAPACK part, right? I mean, that's also the reason why we don't try to compile these ourselves in our FLEUR configure script. You really have to provide these, and you should provide not something self-compiled just from MATLAB, but you really should try to get an efficient version here. And if you don't have anything from your vendor, probably something like Open BLAS or so might be a good starting point. Okay, and with this, I would like to thank you for your attention, and I hope you will have lots of fun with FLEUR, and I hope you can manage to use this information here to find a suitable setup for your parallel calculations.